hypothesis testing in regressions, and how heteroscedasticity will change that. So we do, in a very simplest regression, we would just have one coefficient. Now, a lot of our hypothesis testing is on several regression coefficients. And, there's an important distinction between doing a t-test on an individual regression coefficient versus doing an f-test on a set of regression coefficients taken together. In the extreme version, sometimes we just do all of the slope coefficients. Now, in the univariate regression, the t-test on significance gives the same p-value as the f-test. That's a relief. They will come out and give me the same answer. Because, the f-test is whether all the x variables jointly are different from 0. In a univariate regression, there's only that one variable, and the t-test is whether that's singly different from 0. In a univariate regression, all of them is the same as just one of them. But with a multivariate regression, the f-test is testing whether a whole bunch of slope coefficients are all of them, each and every one's not 0. So again, remember from the univariate case, a 0 slope of the regression just says there's no relationship. Y might go up and down, x goes left and right, but there's no relationship there. 0 slope. In the multidimensional case, lots of x variables, the intuition of 0 slope generalizes there too. So often we want to form tests about whether a group of beta coefficients are all equal to 0. It's different than testing if they're one at a time different. For instance, if we have a bunch of dummy variables for education, we might want to test whether education overall is useful in prediction, not necessarily whether one of those education coefficients is different. So that can be done with the linear hypothesis package in R. Let's step back a little bit and think about how these tests are generally set up. We measure the accuracy of a model with the sum of the squared errors. Remember back when we introduced ordinary least squares and explained the procedure was to minimize the squared errors. Make the squares least. That's the ordinary least squares. Each error is y minus the predicted value, which is based on the model, then squared. Model coefficients are chosen to make those squared errors as small as possible. So an accurate model has a smaller sum of squared errors. If I add one or more x variables, then the error is certainly not going to increase. At worst, the new x variables might be totally useless, but in general, even if they're random numbers, they might improve things a little bit, which is a bit of a problem. A rule of add x as long as it reduces the sum of squared errors would be no good. Instead, I have to ask a bit more sophisticated question. Did the sum of squared errors go down a lot? Is that a big reduction in the sum of squared errors? This goes back to what McCloskey identified as the classic statistics problem. How big is big? Is there a big difference in the sum of squared errors between the two models where one of them has more x variables? Or as an economist might put it, if adding more variables has a marginal cost, then how large is the marginal benefit? Rational decision making has to make a trade-off. Compare the marginal benefit with marginal cost. Adding x variables makes the error smaller. Dropping x variables makes the error bigger. What's the best choice? Adding a set of variables and asking about their marginal benefit in the model is often done in cases like where I have a set of dummy variables, such as education. Now, a final note, which I've reminded you before, is statistical significance is not identical to importance. It's quite possible that things could be important even if they're not statistically significant, or vice versa. They might be statistically significant, but unimportant. We have lots of nice mathematics about statistical significance, but we do not have nearly so much about actual importance. That takes judgment. Looking a bit deeper at the formulas, the sum of squared errors, sometimes called sum of squared residuals, is the sum of each error term squared. Each error term, y minus beta hat value times x. So when we compare two models, we typically assume one is nested within the other. It's a proper subset with fewer x variables. The sum of the squared residuals for the base model with fewer variables, that's SSR naught. Then the model with more x variables, that's SSR1. So SSR naught must be larger. Few variables means larger errors. We can find the percent change in the sum of squared residuals, so that is, in some sense, the benefit of adding more x variables. But note that squiggly equal sign. This is an approximation. To make it better, we'd want to add something more like an elasticity than just a percent change. We want to take the percent change in the sum of squared residuals, divide that by the percent change in the number of x variables. In this notation, the base model has k x variables, while model 1 has k plus q x variables. Model naught has n minus k minus 1 degrees of freedom. Model 1 has q more variables, and so q fewer degrees of freedom. That means the percent change in degrees of freedom is given there in that formula. Divide the percent change in sum of squared residuals by this percent change in number of x variables, and that gives us an F statistic. The formula is complicated enough. It's only exact if we have homoscedastic errors. In the presence of heteroscedasticity, that formula is going to get even uglier. So let the computer do the calculations. But it's useful just to keep in mind the basic insight that this complicated formula is at base like what we did back in Principles of Economics. We're finding just an elasticity. Now I mentioned heteroscedasticity. It's extraordinarily common. It means that in a regression line, the errors get spread wider or narrower depending on the value of some x. Classic case is looking at people's wages as they get older. They tend to spread further out as people get older. Recent college grads tend to get a pretty narrow range of offers, conditional on major, but then their wages spread out over the span of a career. Some people get on the fast track, others not. We see that as heteroscedasticity. There's a wider spread of wages among people with a higher age. In the Stock and Watson textbook, they always use heteroscedasticity consistent errors, sometimes called Eicher-Huber-White errors after 3 of the authors who developed those. As you read econometric studies, you might also see HAC standard errors, which are heteroscedasticity and autocorrelation consistent, sometimes called Newey-West for those authors. The formulas are ugly and require some notation from linear algebra, but you should have R do the difficult work and use the COEF test to use the heteroscedasticity consistent standard errors. That does not change the coefficient estimates themselves, only changes their standard errors. Although in turn that does change the t-stats and therefore the p-values that are calculated from that. Usually the standard errors are going to get larger, which means the t-stat goes down and the p-value goes up. So statistics that might look statistically significant become insignificant. Sorry.